We will now discuss the other test using the chi-square distribution for qualitative data analysis. It's called the independence test, also known as the test of association. And essentially, it tries to determine if there is a link, if there is an association between two variables. So, test of association, basically, it's trying to check for an association between two variables. Now, in the past, we have worked with data from two variables and we represent them on a frequency table, which is also called a contingency table. So I'm going to first go over what a contingency table is. Again, this was something that was taught as part of Statistics 1, but in case we need a review, let's go over what a contingency table is. Here we see a 4 by 3 table with 4 rows and 3 columns. And along the rows, we see 4 marital statuses. So there's single, married, widowed, and divorced. And for the columns, it represents drinks per month. And the categories for drinks per month are abstain, that means those who never drink, and those who drink 1 to 60 per month, and those who have over 60 drinks per month. Right? So this contingency table of marital status and alcohol consumption for 1,772 randomly selected US adults is what is displayed here. So the sample size here, N, is this value 1,772. And the way to interpret this table is that there were 67 people who responded, or rather who were single and never drink. All right, so single and abstain. There were 67 observations of that. Then there were 411 observations of married individuals who never drink. Likewise, this value 74 means there were 74 individuals or 74 observations of people who are in the marital status of single who had over 60 drinks per month. So here we see that the values inside this rectangular block is what's called a joint value. All right, it's a joint frequency. That means it tells us observations that meet two variables, single, abstain, single with 1 to 60 drinks per month. Now this value in this last column here, total, this total represents the total number of people who are single, irrespective of whether they abstain or have 1 to 60 or over 60, irrespective of their drinking habits. The total number of single individuals in our sample was 354. Likewise, the total number of married people, regardless of their drinking habits, was 1,173. Widowed, total number of widowed people, 143. Total number of divorced people, 102. The total in the last row of this table here represent the total number of individuals who never drink, who abstained, and that's regardless of their marital status. That's just 590 are the total number of people, whether they are single or married or widowed or divorced, doesn't matter. There are 590 individuals or observations that responded as abstain from drinking. Likewise, 957 were the total number of individuals or observations who had 1 to 60 drinks per month, and 225 represent individuals who had over 60 drinks per month. So this is how we interpret our contingency tables, this one specifically representing two variables, marital status and drinks per month. Now, with our association test or independence test, what we are trying to determine is if there is an association between the marital status of a person and the number of drinks he or she consumes. Is there a link between the two? Is there any correlation between the two? Is there any association between the two, or they are independent? That one variable has nothing to do with the other variable. They're independent of each other. It doesn't matter whether a person is single or married or widowed or divorced. It has nothing to do with how many drinks they consume in a month. So that's an association that we are trying to test using the chi-square test of association or chi-square independence test, right? Now in this slide, we are going to go ahead and formulate our problem for a hypothesis test. It's the same problem where we are analyzing an association between the marital status of individuals and the person's alcohol consumption patterns of US adults. So our study is focused on US adults only. And we have a sample size of 1,772 residents 18 years and older were included in a random sample. And this is the contingency table that ensued, the frequency table that came out from that study, from that survey. The first step in any hypothesis test is to state the hypothesis, correct? Now, again, these are tests on qualitative data, therefore your hypothesis should be stated as a phrase, as a sentence. All right, there is no measurements that we can take other than that just consolidate the data in a table. We cannot find the mean of qualitative data, we cannot find the median, or we cannot find the standard deviation or variance and all that. So because of that, we have to state our hypothesis with a sentence. Again, this is a test of independence or association, and we first state the null hypothesis, stating marital status and alcohol consumption are not associated. Now, if you're using the word associated, then null hypothesis will state they are not associated. If you're using the word independence, then it's going to say marital status, and let me write it down here. Our null hypothesis is going to say marital status, alcohol consumption are independent. All right. And likewise, the alternate hypothesis will say marital status and alcohol consumption are not independent. But if you're using the word association, then independent means they are not associated, they are not linked anyway. So make sure you add the word not if you're using the term associated. For alternate hypothesis, it will state marital status and alcohol consumption are associated. Right? Now, this was the first step. This is stating the hypothesis is the first step in any hypothesis test procedure. We now go to the second step where we determine the significance level. The significance level is given to us. We tell you at what significance level you're supposed to perform the test, and from there you can determine the alpha value, which is the decimal version of the percentage significance level, right? And after that, this third step involves calculating this test statistic. So we'll go into that in subsequent slides. All right, so this was just to state the hypothesis. Now, here we look at the basic idea, the strategy behind the chi-squared test of independence or test of association. It's the same problem where we are trying to determine if there's an association between marital status and drinking habits, or if they are independent of each other, they are not associated in any way. Now, previously when we were doing the chi-square goodness of fit test, we were working with one-dimensional data. There was only one variable that we were looking at. Here we are looking at two variables. One is the marital status and the other one is the drinking habits, right? The alcohol consumption by the different individuals. And then we are trying to find an association. However, we use the same distribution, which is the chi-square distribution, and all the properties of chi-square that we discussed previously hold true for this test as well. And the formula for the chi-squared is sigma and then O minus E. What is O? O is the observed frequencies that come from the most recent study, right? The observed frequencies minus E is the expected frequencies, and then we square them, the O minus E. We first find the difference between the observed and expected, and then we have to square them, then we have to divide them by the expected frequencies, and then sum them up, and that's going to give us the chi-squared value. We did the same thing when we worked on the goodness of fit test, right? The previous test that we learned for chi-squared. However, for this problem, for the independence test, there's a different formula that we need for E. If you recall, we had used this formula before. E was equal to N times P, but that was good for one-dimensional data for the study we did with one variable, one-dimensional data or one variable. However, here we cannot, because we have two variables, we cannot use this formula, but it's a different formula that we are going to use, and this is what it's going to look like. E equals row total multiplied by column total divided by N. All right, this is the formula we are going to use, and the row total are the total values along the row. That's all, these are the row totals, and these total values are the column totals. All right, the totals of each column. So essentially it's going to be for single abstain, the expected frequency is going to be 354 multiplied by 590 divided by 1772. Just to find the expected frequency, we have to use this formula, and once we find all our E values, we can go ahead and subtract E from O, and then go through the process like we worked through the table in the previous case of goodness of fit test. Right? So let's go through those steps in the next few slides, but I think the next slide is going to again talk about the formula for the expected frequency. And then we'll go through a slide where we'll show how to find the expected frequencies for this data. Now here the formula for expected frequencies for an independence test is being stated formally. In a chi-square independence test, the expected frequency for each cell is found by using the formula E equals R times C divided by N, where R is the row total, C is the column total, and N is the sample size. So let's go on and look at how we calculate the E values for the example that we are working on. All right. Now, before that, we always have to talk about the distribution. It's the same chi-squared formula. For a chi-squared independent test, the test statistic chi-squared equals sigma O minus E whole square divided by E has approximately a chi-squared distribution if the null hypothesis of non-association is true. Again, keep in mind, the null hypothesis is always going to assert that there is no association between the two variables. They are independent. The number of degrees of freedom is R minus 1 multiplied by C minus 1. Okay, so I'll tell you how to find the value for R and for C once we go into the problem. But remember, it's the number of rows minus 1 multiplied by number of columns minus 1, and you multiply them. All right, you are multiplying the two values, where R and C are the number of possible values for the two variables under consideration. So here is our example, and we'll show how we can calculate the E values using this formula. All right, so the initial values given to us, the 67, these values in black, 67, 213, 74, these are the observed frequencies. All right, these are the observed frequencies. We have to find our E values, and remember E is given by the formula R multiplied by C over N, where R is the row total multiplied by the column total divided by N. So when we want to find the E value, the expected value for this particular cell, where number of observations for single and abstaining individuals was 67, what would be the expected frequency? So you have to look at the row total, which is 354, and that's what we have here, multiplied by its column total, which is 590, divided by N, which is the total sample size, 1772. And you have to go through each of these cells one by one and find its corresponding expected frequency. So how did we get this 191.2? We went to this row total, which is 354, and multiplied 354 by its column total for that cell is 957 divided by 1772. So 354 times 957 divided by 1772 gives us 191.2, which is the expected frequency. Likewise, here the example worked out here for the cell, which is about widowed people who had 1 to 60 drinks per month. That's observed frequency was 51, but the expected frequency is a calculated value again, which is row total 143 multiplied by the column total, which is 957 divided by 1772, and that gave us a value of 77.2. So all these values here in red, and this one in green, and this one in blue, these are expected values, expected frequencies obtained by multiplying the row total with the column total and then dividing by the total sample size. So we have to go through each of these cells finding the expected values, and once we find all our expected values, we can do O minus E for every cell, and then we have to square the difference, and then we have to divide that by E values, and eventually we sum them up. That will give us the test statistic chi-squared value. So we'll go through the entire exercise in the subsequent slide. Now here we present another way of calculating the chi-squared. It's the same process, but instead of working through a table, we are just doing the calculations all at once and adding the values as we go along. So it's O minus E whole squared divided by E, and that's exactly what they are doing. So we have for the first one 67 minus 67 is the original, the observed frequency, and 117.9 is the calculated expected frequency. So 67 minus 117.9 whole square divided by E. Correct? That's in the formula, so divided by 117.9. Then for the next one, it's 213, which is observed, minus E, which is 191.2. Then you have to whole square that, divided by 191.2. So they are doing that for every cell, and as they go along, they are adding it to the previous calculation, and we end up with a chi-squared value of 94.4. Now the only problem is that if you use a table, then it is more systematic and you make sure that you don't miss a cell. But you can do it this way too, as long as you show all the calculations here. All right, show all the additions of every cell, and then once you sum them up, you get your chi-squared test statistic value, which is 94.4. But for the test, I'm going to give you a table anyway where you can work one by one the steps and list all your O values in one column, then the E values in the next column. You can do O minus E, and then in the column after that you can square those values in the previous column, and in the last column you divide O minus E squared whole square divided by E and then add them up. It's up to you. all right, as long as you get it right. So now that we have calculated our chi-square test statistic value, let's see what the next step is to perform the hypothesis test through the two approaches we learned, the critical value approach and the p-value approach, and then finally to come to a decision. All right, so I think in the next slide we will go through the steps first, and then we will work this entire problem in the next few slides. So here is the summary of the steps to perform a chi-squared independence test to decide whether two variables are associated or not. What are the assumptions? All expected frequencies are 1 or greater. At most 20% of the expected frequencies are less than 5. These are the same assumptions as we had for the goodness of fit test, and of course simple random sample goes for any statistical study. Step 1, the way we state our null and alternative hypothesis, keep in mind it's written out as a sentence. Null hypothesis will say the two variables are not associated, or you can say the two variables are independent. And the alternate hypothesis will say the two variables are associated, or if you're using the term independent, then you should say the two variables are not independent. Step 2, you decide on the significance level alpha. In step 3, you compute the value of the test statistic. Chi-squared equals sigma of O minus E whole square divided by E, where O and E represent observed and expected frequencies respectively, and we denote it with the symbol chi-squared sub 0. And then in the next slide, we use the critical value approach or the p-value approach or both. Again, keep in mind this is a right tail test. Chi-squared curves are all right skewed curves, and draw your diagram accordingly. Your diagrams should begin from 0 and then go up and peak a little bit towards the left and then have a long tail. And the reject region in a critical value approach is always going to be on the right, because chi-square tests are all right tail tests. So you have to find the chi-squared of alpha value. You don't need to split your alpha for a right tail test or for any one tail test. So you find your critical value, but that's going to be a chi-squared value, and then you bring your test statistic value and see on which side it falls, whether it falls in the reject region or the do not reject region, and then take a decision accordingly in step 5. For the p-value approach, again, you start with your test statistic value, and then you find the area to its right for a right tail test, and that area is the p-value. And once you find your p-value, just compare it with alpha to see if it's less or equal to alpha or not. If it is less or equal to alpha, then you reject your null hypothesis. Otherwise, you do not reject null hypothesis. And finally, you interpret the results of the hypothesis test in context of the problem. All right, so these are the steps. Now let's work that association problem example of figuring out whether there is indeed an association between marital status and alcohol consumption for the rest of this chapter. So the question here says, at the 5% significance level, do the data provide sufficient evidence that an association exists between marital status and alcohol consumption? Now, you can check your assumptions first before proceeding. Are expected frequencies 1 or greater than 1? Yes. If you look back on the calculated expected frequencies, they are all greater than 1. Then at most 20% of the expected frequencies are less than 5. Again, if you go back and check the expected frequency values, they are all greater than 5. And then is it a simple random sample? Yes, the question says here a random sample of 1,772 residents, which tells us it's a simple random sample. So all three conditions are met. So we can say that we've checked the assumptions and all assumptions are met. All right, so then the next step, we state the null and alternative hypothesis. So for the null hypothesis, we are going to say in context of the problem. Marital status and alcohol consumption are not associated. Or again, if you're using the term independent, you can say they are independent. All right. For the alternate hypothesis, you're going to say that they are associated or they are not independent. So marital status and alcohol consumption, let me write that, consumption are associated, that is, they are not independent. But you can use either of these terms, but make sure you're stating it correctly. Okay. Decide on the significance level. They tell us to perform the test at 5% significance level, so alpha is going to be 0.05. So let's go on to the next part where we calculate our test statistic. Now we've already done that in a previous slide and we came up with the test statistic value of chi-squared sub 0 as 94.4. Again, go backtrack a little and view that slide where we showed all the calculations at once and we did our O minus E, found the whole square, divided it by E, and then added the subsequent values that way, and we came up with a chi-squared test statistic value of 94.4. That was our evidence. Now, in the next step, we are going to perform the critical value approach test first, but first we have to calculate our DFs. So let's look at our DF. It says R minus 1. So the marital status were the rows. We had 4 marital statuses. They were single, married, widowed, and divorced. There were 4 of them, so R is 4. And there were 3 columns, right? Abstain, 1 to 60, and over 60. So for alcohol consumption, there were 3 categories. So when we calculate our DF, it's going to be 4 minus 1, R minus 1, so 4 minus 1 multiplied by 3 minus 1. So that would be 3 times 2, which would give us a DF value of 6. All right, let's draw our diagram for the critical value approach showing the reject and the do not reject regions. So here is our chi-squared curve. Again, it's always going to be a right tail test, therefore our reject is going to be always on the right hand side. Do not reject on the left hand side. So this is our critical value, which is going to be chi-squared of 0.05, the significance level, right? Because this area corresponding to the reject region is 0.05. All right, so we have to refer to the chi-squared table, which is table number 7 in our formula sheet. That value is going to be based on a DF of 6. So chi-squared of 0.05 with DF equal to 6. If you look up your table, it's going to be 12.592. Let me use a different color to indicate that it's 12.592. So critical value is whatever value chi-squared of 0.05 with DF equals 6 turns out to be. That value is 12.592. 12.592. All right, you can either get it from your graphing calculators if you're using one, or the table will give you the exact value. So now we bring our test statistic value. Our test statistic value was 94.4, correct? So 94.4 is greater than the CV of 12.592. So it's going to fall way to the right of the cutoff, right? Maybe somewhere here. Let's use a different color. So let's say that's where 94.4 is, and that is the reject region, correct? It falls in the reject region. So let's write that. Falls in reject region. So our decision is going to be reject null hypothesis. Therefore, decision will be reject null hypothesis. Now I'm going to perform the test using the p-value approach as well and see if we get a decision of reject or not. Now, to use the p-value approach, recall that we start with our test statistic value. So let's draw the curve again. So here we have our chi-squared curve beginning from 0 and then peaking towards the left and then extending all the way to the right. And we first have to locate our chi-squared sub-zero value of 94.4, which is the test statistic value, correct? And 94.4 is a pretty large number, so it's going to fall way to the right. So let's say, for the sake of showing it on the diagram, it's somewhere here, 94.4, and it's going to be the area to the right, and that is going to be the p-value. Because it's a right tail test, the p-value is going to be the area to the right of the test statistic value of 94.4. Again, what is the p-value? The p-value represents the probability of finding a test statistic and evidence of 94.4, assuming that the null hypothesis is true. So when I calculate it, when I find the p-value for 94.4, let's write what we are doing here. Find area to the right corresponding to chi-squared value of 94.4 with df equals 6, and that value is a very small value. It's 0.0005 really. All right, it's a very small value. Naturally, 94.4 is a pretty large chi-squared value, so it'll be way to the right, and the more you go to the right, it's getting closer and closer to the horizontal line, so it's approaching 0. All right, so that's why we have a very small value for our p-value. So this was the first step. Our p-value comes out to be 0.0005. So in the next step, we compare p and alpha. So p is 0.0005 is definitely way less than 0.05, which is our alpha value. Therefore, whenever it's less or equal to alpha, the decision should be reject null hypothesis. All right, so we get the same decision using the p-value approach as we got using the critical value approach. So our final, well, it's not really the final step. We have another step to interpret our study, but the decision is reject null hypothesis. We came to that decision using both the approaches, but do not forget to interpret that final step, right? So if you miss interpreting your test after all this work, you will lose quite a bit of points. All right, the interpretation itself on the tests are assigned 4 or 5 points. Okay, so interpretation for hypothesis tests, you always begin with the significance level. So you say at the 5% significance level, that was the significance level that we were testing. At the 5% significance level, the data do provide, if it's reject, you always say that your data was strong enough. The data do provide sufficient evidence to conclude, and then I'm going to use the verbiage from the question, sufficient evidence to conclude that an association exists between marital status and alcohol consumption. So just use the verbiage from the question, all right? You don't have to think too much about it. To conclude that an association exists between marital status and alcohol consumption.